2, graph the function. What we're looking at here is an exponential function. Exponential functions have these shapes. They either go like this or they go like this. They do flatten out, so they kind of have it's called a horizontal asymptote. So that means it's a space where it's not going to cross horizontally. So in other words, it doesn't go like this, going down forever. It flattens out, levels out at some point. It doesn't go beyond that. So basically what I want to do is I want to establish where this specific graph is going to be. And the fact that x is up in the power, that's what we're doing here. So we're going to be evaluating some powers of x. What I want the power to be is -2, -1, 0, 1, and 2. Those are the powers I want. If x is the power, that's just simply what I pick for x. If they gave me some different power, let's say they said y equals 1/2 to the x plus 3 power. Let's say it was that. And I want my powers to be -2, -1, 0, 1, and 2. I have to add 3 before I get those powers, right? So if I want the power to be -2, x would have to equal -5. -5 plus 3 is -2. -4 plus 3 would be -1. -3 plus 3 would be 0. So the x's I pick would be -5, -4, -3, -2, -1. All right? But for now, I'm pretty sure they're going to stick to x being the power, so this will probably be our list of powers we're going to do each time. Now, let me start with the 3 easy ones. Specifically, these 3 here. Those 3 powers are very, very easy to evaluate. Each one does a specific thing. The negative first power is called the reciprocal power. It makes the reciprocal of the base. What's the reciprocal of 1/2?
-1/2.
What's the reciprocal of 1/2?
2 over 1.
2. Alright, so 1/2 to the negative first power is 2. Okay, I didn't need a calculator for that. -1 power just reciprocates the base. So if it was 8 to the -1, that'd be 1/8. 3/17 to the -1, 17/3. 1/14 to the negative first, 14. So real simple. The 0 power is always equal to 1. So 1/2 to the 0 power equals 1. 500 to the 0 power equals 1. 77 to the 0 power equals 1. Rhinoceros to the 0 power equals 1. Platypus to the 0 power equals 1. Dog to the 0 power equals 1. W to the 0 power equals 1.
Whipperdill?
Whipperdill to the 0 power equals 1, yes. Alright, so 0 power is simple, equals 1. The first power is whatever the base is. 1/2 to the first power is just 1/2. If I'm graphing, I like decimals over fractions, so I'm going to go with 0.5. If you write 1/2, it's not wrong. Alright, the -2 and the +2 powers are just this number squared and that number squared. So 2 squared is 4, 0.5 squared is 0.25. So if you evaluate these first, square that to get the -2, square that to get the +2, and all of a sudden you've got all of your points that you need. And then if I just plot those 5 points on my graph, I've got -2, 1, 2, 3, 4. I've got -1, 2. I have 0, 1, 1, 1/2, 2, 0.25. Now, I've already told you that the graph is going to flatten out as it goes one direction. So this one looks like it's coming to the right, flattening out as it goes off to the right. The flattening out happens exactly one space below wherever the 0 power happened. So, the 0 power got me 1, right? One space below that 0, so that's where the flattening out is going to be. So I'm going to put a horizontal line here as a boundary. The official name of this horizontal line is a horizontal asymptote. I didn't create the name, I just know what it's called. A horizontal asymptote. That is something drawn in a graph. It acts very much like a pretty high-powered electric fence. The graph does not want to cross that fence. Okay? There's also what's called vertical asymptotes. This graph doesn't have any, but that'd be a vertical line where the graph would not want to cross it. If I connect the dots, as I connect the dots coming this way to the right, I want to make sure that I do not cross the asymptote, that instead the graph just kind of goes along it like so. Alright? and that will be how you graph that. You don't have to write the words, but do give me the dashed line there. Again, wherever the 0 power happened, whatever value that was, go one space below it. That's where the horizontal asymptote lives.